The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show. Karen, have you ever heard about the Atari Punk console?
Okay, I got the first word, Atari, and I know punk, but I've never heard Atari and punk used in the same sentence.
Right, so it's not an Atari with a bunch of nose studs and a mohawk.
Listening to Billy Idol?
Right, it's different than that. So what people do is they take 555 timers and they combine them to create a simple circuit that can make Atari-like music and sound effects.
So they don't actually use any part of the Atari, they just make it sound like an Atari.
Right, it's actually a lot cheaper to just use 555s than to actually get Atari parts.
Okay.
Yeah, so what I was thinking is we could build something like that ourselves. You know how we made that laser harp a while back? We could build an Atari Junk keyboard.
Oh, and we could be cool piano players like Ben Folds.
Oh yeah. So here's my plan. We'll take the matrix from these keys and figure out how it works. We'll put some discrete logic in, so instead of using a microcontroller, that'd be too easy. We'll actually create a circuit to read the keys, and then we'll feed that input into probably a number of Atari Junk Console integrated circuit pairs, so we could have multiple sound effects and different sound effects playing at once. I don't think I want the whole keyboard, probably cut it in half just to make it a little bit more manageable of a product. So in part one, we're going to get the keyboard matrix working, and then in part two of this project, we're going to attach it to the Atari Junk Console and make music. Let's get started.
Amazing hacks.
Where are my dragons?
Inspired designs.
Oh, look, I knocked some hot glue loose.
Regrettable acting.
I want to live in a world with Star Wars again!
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
The first thing I'm wiring up is an oscillator. An oscillator is different than a crystal in that the oscillator can output its own waveform, whereas a crystal, you need to attach something else to it in order to get a square wave. So this is a 1 megahertz oscillator. I have power and ground going to it, and the other two pins are enable, which I've pulled high, and then output, and that's this pin right here. So if we hook this up to power and then hook up the output pin to an oscilloscope, we should see a 1 megahertz square wave coming off of it. I also added a cap to the voltage between the voltage and ground just to make sure it's smooth. Should always put capacitors on everything. So yeah, let's hook this up to the oscilloscope and see what happens. All right, let's hook up 5 volts to this oscillator. Gonna hook up ground to the scope and get the signal, turn on the oscillator, and let's check the input. Frequency just under, there it is, 1 megahertz. 50% duty cycle. See how the highs and lows are the same. So I think that's going to be a little too fast for a switch matrix. It's not that the circuitry wouldn't operate at that frequency, but things like the state of the buttons, that actually might be too fast of a sample. It might not give us an accurate value. So we're going to divide that. So I've added a binary counter. What these things do is there's an input clock pulse. Every time there's a clock pulse from the oscillator, it's going to clock that. And this output goes 1, 1, 1, 1, 1, 1, 1, and then resets. So basically a high output moves down the line of this. So later on in the circuit, we're going to use that to actually drive the keyboard columns. But for right now, I'm going to use it to divide the circuit. So if it takes 10 pulses to get to the end, that means we can put the clocks from the oscillator into the binary counter and get a divide by 10, which would give us, what would that be? 100,000 hertz. Let's see if it works. All right, so we're going to take the clock output of the oscillator and put it directly into the clock input of this decade counter. Decade counter is basically a shift register that loops back upon itself. So we have power, ground, master reset is disabled, chip enable, clock input, and the rest of these, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then carry are the actual outputs. So we're going to want output 9, since that will be the end of the chain. Actually, any one of them would work because they're going to activate at the same frequency. So yeah, I guess we could just test them that way. We don't have to necessarily wire something up. Voltage, ground, clock pulse 1 megahertz. Let's check one of these random things. There it is, 100 kilohertz. We use the decade counter to divide by 10. So we can use this as the base clock for our switch matrix because it's going to get divided by 10 again because we're going to run it through another decade counter, which means the fastest frequency of actually sampling all the switches will be 10,000 hertz, which is still much faster than it actually needs to be. But it's the easiest thing to divide to. I've added a second Johnson counter to this. Here's what's going on. The first Johnson counter, one of the outputs is going into the clock input on the second Johnson counter. And then instead of going from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm actually attaching 8 to master reset. So once it gets past 0 to 7, it'll reset itself. We don't really have to do that, but I figured it would be kind of cool. That way it's only counting 0 to 7 column lines like it's supposed to. Let's take a look at it on the scope now. Turn on the power. All right, so here's the input, 100 kilohertz. Now if we look at the 8 line, see how it's really short? Basically, as soon as it triggers, it causes a master reset. So that happens pretty quickly. See how short that pulse is? Yeah, see, it's very, very quick. So the timing isn't exactly perfect, but it's pretty close. In fact, we could probably take a look at that by turning on channel 2. Let's see the difference. Okay, here's position 8, and that will trigger number 2, which is here. So see, it goes back to 0 very, very quickly after number 8 is triggered. So for all intents and purposes, it happens instantaneously. I mean, you're talking like nanoseconds of time. Let's take a look at the output. It should be 100 divided by 8, 12.5 kilohertz. That's good. So these should work all the way up to 7, which is this pin. Yep, 0 to 7. And then when it gets to 8, it resets, which means 9 should never occur. Yep, flat line, nothing on 9. Okay, so based off our early schematic, the thing we're going to do next is hook up the outputs of this Johnson counter to 2 different things. An inverting buffer that will drive the columns, as well as the flip-flop driver that will actually load the data off of the switches. Okay, so I got this inverting buffer off element 14. It only comes in surface mount, so I'm wiring it to this adapter so I can put it onto my breadboard. And then we can continue. So when we did the switch matrix demonstration with the microcontroller, the active column was actually low and the rest of them were high. So I'm using this inverter so we can invert the output from the decade counter and create the same kind of condition we had with a microcontroller. I mean, obviously it's easier to use a microcontroller, but this is kind of fun. It's like, let's do the same thing with discrete logic. I mean, we can make it even worse. We could do it with just like transistors. Oh, that would take forever, and the board would be like the size of the moon. Here's what we have so far. Oscillator, drives decade counter, and this is going to go into the buffer. So this is an 8-bit inverting buffer. So instead of seeing peaks from the decade counter, you'll actually see dips as it goes low, just like we saw with the switch matrix. So I'm going to wire this decade counter up to this buffer, and then the outputs of this buffer are going to go to the switch columns. The inputs here also have to go to the flip-flop, so I need to wire this in such a way it can be a bus, so we can go from here to someplace else, etc., etc. Yeah, but that should work. So we'll probably have the switch connector for the columns here, and then the rest of the circuit will go down here. Time for some boring wiring. All right, I've attached the buffer here. So the outputs of this Johnson counter are going to the inverting buffer. So what comes in here will be inverted here. Let's take a look at it with the scope. There's the input and there's the output. They're inversed. Cool. All right, so that means the outputs look all like this. There's the first one, there's the second one right after it, and then the 8th one. So the 8th one is right before the before the first one again. So yeah, this pretty much matches up what we were doing. Well, it exactly matches up what we were doing with the microcontroller, where we're going from 0 to 7 on the column line, and this is what drives the active column. So what happens is when you push the key, the current sinks into the buffer, pulling the key low, and that's what tells you that a key has been pressed. Yeah, all right, so I'm going to add a header to this, and that will be our column driver, and then I can get started on the key reader portion. And that portion is a little bit more complex. Originally, I was going to take this bus of signals here and use that to drive the switch flip-flops, but I'd have to wire up the wires twice, which is kind of sloppy to do. Also, it's a lot of extra work. It might actually be easier just to add another Johnson counter over here and have it be clocked the same time this one does. So they're basically clocking them in parallel. And we could do that with a delay line. I was going to put a delay line between every one of these inputs, but again, we could just have a single delay line and a single Johnson counter driving the input switches. The reason I want a delay line is because I want the switches to have time to stabilize once the column activates before we actually sample their values. So I'm actually going to cut the pulse in half and give it like, I don't know, what would that be, 20 nanoseconds of time to stabilize? So yeah, I think I might do that. Might add another Johnson counter. So basically we have the oscillator, Johnson counter to divide it, and then we'll have two Johnson counters being clocked in parallel. One drives the columns, one drives the flip-flops, but the flip-flops will be slightly delayed.
The Warp 7 is a tiny development platform that's ideal for developing wearable technology and Internet of Things products. Use the Warp 7 to build wearables such as activity trackers, smart watches, or smart clothing. You can even use it to build innovative IoT products for smart home, city, or industrial applications. Purchase the Warp 7 development platform on element14.com today.
So I was going to use a delay block line to give us a slight delay from when we activate the columns and then read them on the flip-flops. We couldn't get it working in time, so I think I'm going to do something else. What I will do is use the terminal count and the individual pulses of our divider Johnson counter. So what I realized was we need a little bit more time than 1 microsecond, which is what each one of these pulses would be. So what I did was I started driving the line or the column lines with the secondary Johnson counter using the terminal counter as the trigger right here. So it still happens at the same frequency, but the pulse is much longer. Then what we can do to make sure that the line is asserted before we read it into the flip-flops is use one of these pulses to actually clock in the data into the flip-flop. So we use the terminal, we go low, the switches are active, we wait for them to be valid, then a few clocks later we use this edge to actually read into the flip-flops. So we can use the same divider Johnson counter to do two things with the delay and not have to add an extra circuit. So we're actually using the terminal count pin to actually drive our column counter, and then we'll probably be using, I don't know, 7 or 8. Well, actually, the terminal count goes low here and then high. So if we actually want to drive the other one, we should probably use something after the rising edge and not after the falling edge. So we should probably use like 2. We can hook up to the scope and make sure this will work before we add the next counter. Okay, take a look at the scope here. Here's a normal pulse on the Johnson counter, and then here is the terminal count pulse. See how it's much longer? Here we can take a look at the difference of them. See that? So what I think we can do is we can use this clock to drive the column, and then we can actually clock in the actual switch data into each flip-flop using either this clock or this clock. So see how the second one, the blue one, is a little bit after the rising edge of the yellow one? That will give the switches time to stabilize before we actually read them in. Okay, so I'm going to add another Johnson counter, and we're going to use that to drive the flip-flops. All right, to go over this again, our Johnson counter that divides the frequency, we have the terminal count going and driving the column driver. Then we have the number 2 pulse, which is actually the third pulse, going and driving the clock of the, I guess what we'll call the row or flip-flop counter. And then we have the flip-flop counter also resetting itself on the 8th pulse. So this should give us a signal now that we can check out on the scope. I'll get it wired up and we can take a look. Let's take a look at the scope. All right, we're gonna look at the third counter on the column. There it is. Now we're gonna look at the third counter on the switches. Aha! Okay, we have a slight delay. So the flip-flops will load the switch input slightly after the column is asserted. So we're able to do this without the delay block integrated circuit, just using the existing Johnson counters that we had laying around. Although now we have 3 Johnson counters in this circuit, but I swear that's all we need. We don't need any more. So there's 6 switch inputs because there's 6 rows. So that means we need 8 flip-flops, and on each flip-flop, only the first 6 bits will actually be used for anything. The top 2 bits will be unused, but that's fine. So I've got to wire up a big bus, basically, of all the switches. So the 6 switches will go into all 8 of the flip-flops, but only one of the flip-flops will be allowed to load at a time based off the clock pulse. And that clock pulse will be derived from this third Johnson counter. It should work. Actually, I've never built a circuit like this before. You know, I've programmed switch matrices, so I assume this should work. I mean, I would say there's at least a 51% chance it'll work. There's definitely a very slim chance of survival, Egon. All right, well, I'm gonna add some flip-flops and then we'll test again. It's time to attach the 8 octal flip-flops. So octal flip-flop, that means 8 bits per flip-flop, although we only need the first 6 bits of each flip-flop to line up with the rows of the switch matrix. So 6 times 8 is 48 keys. That matches up. Okay, I'm gonna attach the output enable line on each one of these flip-flops, and then I'm gonna go through and attach the clock line from the secondary Johnson counter. So this will actually tell the flip-flops when they should be loading data. So the switch matrix will be attached to all 8 of the flip-flops, so only one flip-flop at a time will be loading data off of the switch matrix. I wanna make sure I wire all these things nice and straight, kind of like a circuit board, because there's a lot more wiring to come, and we need to keep it neat. I've attached the first 6 bits of each flip-flop to this output header, and that's actually what's going to go to the portion of this that creates music or noise or whatever it's going to end up being. So on the original keyboard here, the columns were scanned like this. Doot, 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 doot. And then the keys were scanned like this. Doot, 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 doot. Well, you know, so that key in pairs. These 8 columns represent the 8 shift registers, right? So then we have 8 more, 8 more, 8 more, 8 more, 8 more. But we're only using the first 6 bits of each shift register for the switches. So I've attached all of the outputs to our output header bank down here. Now what I have to do is attach the matrix switches themselves in a bus to all of the flip-flops. So what happens is, as the counter loads each flip-flop, a different set of switches will be put into the outputs. And the flip-flops are basically RAM, so the output never changes except for when it's clocked in. So if the flip-flop's not active, its lights or output will not change. So now I have to wire up a boring bus. But once I do that, we should be able to give it a test. Now I'm going to attach the 6 rows of switches to each one of the flip-flops. So this has to be done like a bus, so they're all connected together. But again, only one flip-flop is going to be active at a time, so if the flip-flop is not active, it will ignore the signals coming in. So this is very much like a data bus on a computer, where the data bus is actually connected to everything, but only certain devices will respond to it. So once I get all the wires wired across the board, I'm going to bring them up to some pull-up resistors, which will give them a known state. And then this connector that I'm wiring right now is what will actually connect to the rows of the keyboard. I completed wiring up the switch sense bus. So it's a bus of 6 bits going across all of the flip-flops, and it connects to the keyboard there. Now I didn't hook up all 48 LEDs because that would be a pointless waste of time. We only need a couple to get the point across. It's got this one on 0, so we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that will separate them. Felix is working on the next part, which is using these inputs to actually create the music. So if I can get this working, then we can combine the things we're working on. All right, let's see what happens when we turn it on. Okay, so these buttons are active low, which means they're normally high. All right, so it's basically these go in the same line as the keys. So if I push this key, this LED should go off. First key, good. All right, same column, different row, also good. Scope is showing a clean transition, no jitter, that's good. Because if this was oscillating on the light, we wouldn't be able to see it, but we'd be able to hear it. It'd be like, you know, like make some sort of weird, dumb sound like that. So we wanted, if you push the button, you know, the Atari Junk Console, meep, keeps making the note. Because it also has oscillation. So if we have oscillation controlling oscillation, we'll kind of have junk, a real junk console. All right, let's test it some more. Let's go to this one, which should be that and that. Let's go a little further. Maybe that and that. All right. We don't need the LEDs in order to make the keyboard, so I'm not going to spend my time wiring up a bunch of them. All right, so this should be second to last and last. Okay, it looks like the keyboard matrix is working. Now we should check in with Felix and see how his music portion is going.
What I've done is taken the circuit from the breadboard and ported it over to this Protoboard. I've also added 6 buttons and 7 potentiometers. One of the potentiometers is adjusting one of the 555s. And then the others, they are connected to VCC, and then the switch, and then it goes into the potentiometer, and then back to pin 7. It only makes noise whenever I push a button here. These other buttons that I have on here, they're not connected. The reason I didn't connect them is because we only had room for this many potentiometers on here. This potentiometer is going to select the octave. We may figure out what the value of each key should be and just set it a static resistor. But so right now, this is how we can tune it. We select the octave somewhere. It sounds great, right? But then each one of these is on the buttons, which will be the keys. So here, so there's that one. But the thing is, per each octave, we're going to have one set of 555 timers, and each octave there can only be, it's not going to be polyphonic in between, within the octaves. So for example, I push this button, I push that one, but if I press them together, it's like a third note. But then if you add another one, it's between the octaves there will be polyphony. So the output from the interface that Ben made for the key matrix is an active low. So I need to figure out how to interface with that using a PNP transistor. I'm going to figure that out now. I've added some PNP transistors to take place of the switches that I have on here. Now we can get input from the keyboard matrix that the interface for the keyboard matrix you made.
Yeah, since my output is active low, that will activate a PNP transistor, causing it to act like a switch, turning on his circuit. So we just have a couple notes hooked up here, but again, if one works, they all work. Ready?
Yep. Let's see, which one is that? Is this one? Oh, it's this one.
I kind of like that where it was like, that's weird. It's like a helicopter. The important thing here is that we got the manually matrixed switches to communicate with the Atari Junk circuitry. I think what we should work on next is figuring out how many of these Atari Junk circuits that we need. Like maybe we could have, each octave could be like a different type of sound effect. Mm-hmm. So we could have like a potentiometer to adjust each one and then 12 notes in each octave. That way you could have a bunch of funky things going on.
Yeah.
Because it wouldn't be a big deal to build 6 of these, right?
No.
Okay, that's what we should do next. That's all the time we have for today. To recap, in part 1, we manually wired a switch matrix driving circuit that will read 48 keys and output them TTL voltage levels on that bus right there. In part 2 of this episode, we're going to cut this keyboard in half and make a cool enclosure for it, including an audio amplifier, and then create 6 copies of the Atari Junk Console circuit so we can have one sound bank per octave.
So go on the Element 14 community on element14.com/TBHS to tell us about your music hacks.
You can also go there to read about other upcoming episodes, builds, and special events. We'll see you next time. Let's play some music. Play Salieri.
Cool, we could be like some famous piano player.
Yeah.
Stevie Wonder, that's the name I was going for.
Yes. Oh wait, no, yes. We could make an Atari Junk keyboard.
Ooh, we could be super cool like Stevie Wonder, except not blind.
The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.